Now let us talk about the graph. Now fractional flow is somewhat similar to permeability. We have fractional flow of water in y-axis. It is increasing in this direction. It will the minimum value of fractional flow will be 0, maximum value will be 1, and we are plotting it against saturation, which is the main component in the water flooding. I am removing this equation also. Now the fractional flow of water will be equal to 0 when the saturation is below the critical saturation or connate water saturation, because below critical saturation water cannot flow, and if water cannot flow then its fractional flow will remain 0, and it will increase in this way once it reaches water saturation, which is equal to 1 minus residual oil saturation. In that case your fractional flow will be equal to 1, because oil will not flow, only water will flow. Therefore fractional flow is 1 here. So this is the intermediate curve which we get, and this is the important part about the fractional flow curve. Now let us try to compare different types of curves. And also you can correlate this curve with permeability curve also. There is a permeability in y direction and saturation of water in x direction, which is increasing this way. This will be your connate water saturation, this will be 1 minus SOR, and therefore the permeability of water will increase in this direction. It will become straight line equal to 1 beyond this point. And if we talk about the permeability, relative permeability of oil, then it will be like this. So fractional flow is function of saturation of water. Okay, so we are talking about different comparison of different fractional flow curves. So this is your fractional flow of water and saturation again. Now we have to figure out that which curve, specifying some condition, that which curve is more beneficial to us. Now at a specific saturation, let us draw a line. The saturation of water is constant here. Let us say FW1, we mark it as FW2, and this will be your FW3. So FW1 will be the most beneficial to us, it is the most beneficial case. FW2 can be thought of as an intermediate case. I am not talking about the values of FW, but talking about the beneficial case. Now if we compare the values, let us compare the values. If we compare the values, that then FW3 is maximum, FW1 is minimum, and higher the FW, lesser will be the FO. Therefore this case is more beneficial, and this case has more setbacks. Now let us understand the effect of different components. For example, let us compare two different types of reservoir. One is water wet and other one is oil wet reservoir. Now what do you think? Which will be the upward shift? Yes, so you can basically directly say that upward shift is not beneficial to us. If the fractional flow is this way, if there is a downward shift in fractional flow, then you can conclude that that condition is beneficial. And reduction of FW is something which we aim for. So if we compare water wet reservoir with oil wet reservoir, which one of them will be oil wet? So this will be your oil wet and this will be your water wet. In water wet reservoir, the rocks will have higher tendency to absorb the water, so they will not allow much of the water to flow through it. So in this case, in water wet reservoir, oil can flow easily, but in case of oil wet reservoir, the rock will hold the oil, it will have tendency to hold a large amount of oil, and therefore in that case fractional flow of water will be higher. So this is your oil wet and this is your water wet. Now depending upon the viscosity, either you can make a direct correlation with the help of this equation, or you can think of that with a common sense. Now let us take viscosity of water first. If the viscosity of water is high, then FW will be larger or lesser? It will be lesser, of course, because viscosity of water is high, then the flow rate will automatically reduce. If the viscosity of water is less, then water can easily flow, it can easily surpass oil, and but this is the case which we desire, higher viscosity of water, and therefore we perform polymer flooding. So the polymer flooding is one type of chemical flooding. We'll take up that as a different topic, but polymer increases the viscosity because of cross linking, and because of its macromolecular structure it increases the viscosity of the displacing fluid. So you can write it as displacing fluid here. So by increasing the viscosity of displacing fluid, the fractional flow of displacing fluid will decrease and the effectiveness or the recovery will increase. So if your fractional flow is high, fractional flow of displacing fluid is high, then it can easily surpass or bypass the oil. Now let us talk about viscosity of oil. If the viscosity of oil is high, then it will be difficult to push, it will be difficult to get displaced, and therefore in that case FW will be higher. And if viscosity of oil is less, then it will be easier to displace, धक्का देना easy होगा, हल्का है, easily movable है. So in that case fractional flow of water will be less, and you can correlate with this curve also. Upward curve defines inefficient process, that will be representing higher oil viscosity, and the downward shift will represent low oil viscosity. Similarly, you can correlate this with water. Now the next factor will be dip angle. So this is your dipping reservoir, alpha is your dipping angle. In this case, sin alpha will remain positive. Now let me write the compressed form of this equation. Fw will be equal to 1 plus x into sin alpha. We have compressed all those terms into x, and this will become negative, plus 1 by y. So we are only changing sin alpha here. In this case, sin alpha will be positive. This is also called as up dip flow. Up dip. If it is straight, then alpha will be 0, sin alpha will be 0. No dip. And if it is in this direction, alpha will be negative and sin alpha will be also negative. And this is also referred as down dip. Now if we visualize all these flow with the help of one diagram. Now in case of up dip flow, this thing will remain positive. So the equation will remain as it is. Now in case of no dip, this term will become 0. You can say that Fw will become 1 divided by 1 plus y. And in case of down dip, it will become 1 plus x divided by 1 plus y. So the numerator is minimum in this case, which is your up dip. Now f is minimum in case of up dip flow where the numerator is minimum. So this will be your up dip curve. Intermediate will obviously no dip. And this will be your down dip. Because in this case, Fw is maximum. Now let us talk about injection rate. So we will use the same equation again, and there's one minor change that we will make. In this case there will be no effect of injection rate, and so this is your no dip, and in this case sin alpha So the first observation which you can make is that in case of no dip, injection rate will have no effect on Fw, fractional flow. So this is something which you can note down. And in case of down dip flow, where the whole numerator is positive, so if IW is high, then this portion will become small and collectively Fw will increase. If IW is less, then numerator will become large, and if numerator is large, then Fw will increase. So in case of down dip flow, on increasing the injection rate, what will happen? This portion or this term will get reduced, and reduction is something which we are aiming for. So in this case, Fw will be comparatively smaller. If IW is kept less, then Fw will be high. And what can actually happen, that if Iw is very less, then this term will become so large that the numerator will become greater than denominator, and ultimately your Fw will be greater than 1. So this condition is called as counterflow. I am rubbing this portion. In order to visualize counterflow, first of all, this will be the down dip flow and this will be our up dip flow. So we are talking about the down dip case in which injection rate is very less. Now, down dip flow, if the down dip flow is in this direction, then this will be our injector well and this will be our producer well. So you are injecting water in this direction at a very small flow rate, and there will be your oil. Now in this case, in counterflow, what will happen? Because of the gravitational difference, because you are injecting water and its impact is also not very high, injection rate is slow. If it is too slow that Fw becomes greater than 1, then what will happen? The water will simply segregate because of the gravity segregation, and oil, because of the density difference, since it is lighter than water, it will flow in opposite direction towards the injection well. So this is something which we will never desire, as oil is flowing away from the producing well. So this is called as counterflow. So in case of down dip, our aim is to increase or make the injection rate maximum. Now if we talk about the up dip situation, this is the equation which we will talk about. Sin alpha will remain positive in case of up dip. Now in this case, you can see the reverse. If Iw is low, if its value is small, then numerator will become large and it will take out large value from this one. So effectively your numerator will reduce, and if your numerator is getting reduced, then fractional flow of water will get reduced. So this is what we will desire in case of up dip flow, up dip injection. Now in case of, in the situation where your Iw is high, then it will make this negative term smaller in magnitude, and if this negative term is smaller, then the numerator altogether will be larger comparatively, and if the numerator is greater, then Fw will increase. This will be given by upward shift in the curve, and this will be given as downward shift. So in case of up dip flow, we will keep our injection rate minimum. So these are the conditions about the dipping reservoir, but beyond this point we will mostly talk about the non-dipping condition in which our reservoir remain horizontal, and the final equation will reduce to this. So there will be no effect of structure, area, density, and all the petrophysical terms which are present there, not even the flow rate, injection rate. Now whenever you get confused that which term will come where, then you can relate by this simple relation that Fw will be lesser when viscosity of water is high, and definitely viscosity will be in a reciprocal relationship with this Fw, because viscosity of water cannot come here, because ultimately it will come in the numerator. So Fw is inversely proportional to viscosity of water. This is the relationship which you can remember, and you won't be get confused that whether here will be mu O or mu w. So these are the different factors which affect the fractional flow. We have discussed about the derivation and the analytical part about it. You can solve different examples based on FW, fractional flow equation. So we will discuss more about FW in the next class, and we will take one example as well.